Hey everybody, Michael back with you for part two of our introduction to seismographs. This part I wanted to show you actually how a seismologist uses seismographic data in order to find out some important things like the time when an earthquake occurs or the location of the earthquake. And in this case, we're going to use a different type of seismic data, not the analog recording like we showed on that drum recorder a moment ago, but digital recording. So for digitally recording seismographs, they work basically the same way. We have the same sensor, the ground motion instrument, the seismometer that records vibrations, but instead of recording it on a pen, cutting a trace through that smoked paper, we're going to feed that data into a computer and we're going to record it digitally. And that way we can kind of play back the data and look at it in much more detail. So this is an actual real world example from an earthquake that occurred in Indiana a few years ago in the early 2000s and was widely felt throughout south central Indiana. And it happened to be recorded by a series of seismograph stations deployed around the state. At that time, we were operating a network of seismograph stations that were actually deployed in high schools around the state. It was a program called the Indiana PEP Earthquake Science Program. PEP is a name for the Princeton Earth Physics Project. It started at Princeton University, and hundreds of these seismograph stations were deployed around the country in an effort to combine education and outreach with seismological research. So these schools around the state actually were operating research quality digital seismograph instruments in their schools, reporting the data through the internet, and we can use those to actually record earthquakes around the state. So with this program here, I'm going to illustrate in a quick and dirty way how we might use that digital data to locate an earthquake that just happened somewhere in the state of Indiana. So this first example is a digital seismogram from one of our seismic stations. This is from Princeton Central High School down in southern Indiana. And this shape of this seismogram is pretty typical for a nearby earthquake. The data is very quiet, but leading up to the earthquake, the time goes from left to right, just like you're writing on a piece of paper. And suddenly the ground starts moving at this point here. That's the arrival of those first primary waves. That gradually quiets down. And then a few seconds later, those secondary, stronger S waves arrive. And you can see that the amplitude or size of those waves increases. So we're going to use this computer program called Windquake to locate this earthquake, starting by picking the times when those primary and secondary waves arrive. And an advantage of digital data is that we can expand it. So I'm going to click here, I'm going to zoom in on it, and maybe I'll do it even one more time to really focus in on the time when that earthquake began. And I can increase the amplitude here to make it a little bit easier to see. And we can carefully, I'm going to do it fairly quickly now, we can pick the time when those primary and secondary waves arrive. It's recorded up here. So this is the time when the P wave arrived. This is the time when the S wave arrived. It was about 12 seconds apart. So this is 12 seconds time span, and that corresponds to a distance of about 60 miles. In addition, it gives us an estimate of what's called the origin time, the time at which that earthquake began, about 20 seconds before that first P wave arrived. Okay, so that's one of our stations. And this distance, 60 miles, all we know is that it's 60 miles away from Princeton, Indiana, but that could be any number of different places around Indiana or Kentucky. So we're going to take another station here. This is Northview High School in Brazil, Indiana, and we're going to do the same thing. We're going to roughly estimate the time of the P and S waves. We're going to zoom in here a little bit. Let's zoom in again so we can pick more carefully, and we can actually get that time to, if we were doing it carefully, we could do it within 100th of a second or something like that. I'm going to do it fairly quickly here. Again, we get a P time, an S time, a larger time difference which corresponds to a greater distance. So this one is 112 miles or 180 kilometers away from that station. And we get a second estimate of the time at which that earthquake began, and it's close to that first estimate. We're going to repeat on a third station. This is Eastern Green Middle and High School, just a little ways away from Bloomington. We're going to zoom in on that one a little bit, and let's zoom in on it again. Let's crank up the amplitude a little bit, make it easier to see. So here's when my best guess of the first arrival of that primary wave is, and when that amplitude increases here, my best estimate of the S wave. So together, again, we get an estimate of the P time, the S time, the time difference, and then the distance of this station, about 87 miles away, and a third estimate of the origin time. And finally, we'll take our last station, my favorite, of course, because it's PPBLO, that's for Bloomington, Indiana, and that is located in the ground floor of the geology building here at the IU campus, and that also produced a just beautiful recording of this earthquake. We're going to zoom in on it again, and I'll zoom a couple times. And in fact, for this one, I may even illustrate, you could zoom way in and crank that amplitude way up, and I can get that arrival time to within 1/100th of a second. I can scroll through the data here until I see that big increase right around here, and I can pick that to the nearest 100th of a second. Okay, maybe something like there. And again, let's back off a little bit and make sure I got that P and S time picked correctly, because I think I made a mistake. Even seismologists make mistakes occasionally. And let me zoom in and zoom in again. I think I did something a little sloppy there. Here's the P time, here's the S time, and again, P time, S time, this one's at about 105 miles away. Again, all we have at this point is distances from 4 seismograph stations. We have 4 estimates of the origin time of that earthquake, all within about a second of one another, and we can use those to estimate when the earthquake began. But the million-dollar question is, where did the earthquake occur? And this is shown in this map view that I hope you can see now. So what we see here, let me zoom in a little bit. So these are our 4 seismograph stations. Up here in yellow is Northview High School in Brazil. Here in green is the Bloomington IU campus. Eastern Green, just a little ways away, and Princeton High School down here. And you can see around each of those triangles is a circle representing the distance away from that seismograph station. And if you look carefully, you can see they all intersect at a point down here. And as I'm moving my cursor, I can see the latitude and longitude shown here in the upper left changing. So I can get an estimate of the location of that earthquake. It's an estimate. 37.959 degrees north and 87.712 degrees west. That is my best estimate of the location of that earthquake based on those 4 seismographic recordings. It turns out this earthquake was near the town of Darmstadt, Indiana, a suburb of Evansville. Very strongly recorded. It was nearly magnitude 5, did a little bit of damage in the Evansville area, and we could quickly use the data from these digital seismograph stations to locate the origin of that earthquake. So this is a quick illustration of how we can use the data recorded on those seismographic instruments in order to get critical information about the epicentral location, the origin time, and in fact, we can estimate also the depth of the earthquake from these recordings. So together with the visual introduction to the seismographic instruments, I hope you get an idea of how seismologists use the data from those instruments to provide critical information about earthquakes. Thanks.